Everybody see my screen and hear me okay?
It's looking
I'll
good.
just, okay, good. All right, guys, thank you all for joining today. My name is Keith Roberts. I'm going to be joined with Onur Karum, where we are coastal engineers at Baird. And today we're going to be talking about some compound flood modeling with applications in engineering design. And so before I get into more detail about this talk and nature of it, just want to explain what compound flooding is here. And so when we have multiple flood drivers occurring at the same time that are contributing to inundation, whether that be along the shoreline or in a river environment, which is going to be the focus of this talk today. So for example, rainfall combined with high river stage levels, etc. So that's exactly what we mean when we say compound flooding in this context here. Okay, let's see, next slide. It's a little laggy. Okay, so before we get into more detail about the talk, I just wanted to introduce more about who we are and who Baird is. Baird is a company that's been around for several decades now. It was founded in 1981. It's employee-owned, and there's 6 offices located throughout the United States with around 90 employees in total. We are primarily river and coastal engineers, so we do many array of different projects around the world and in the United States. And we're ISO 9001 certified, which means that we adhere to certain quality management services standards. Okay, now that I've introduced who we are, the focus of this event is going to be on the extreme rainfall event that occurred in late May of 2020, May 17th, 2020, which primarily affected Northeast Illinois during this time period and led to significant rainfall, and that led to high river stage values throughout the entire Northeast Illinois area. So on the right-hand side, just to give you some context of what the area that we're going to focus on is this magenta blob. It's the only way that I can really describe it here. And on the background here, you see the rainfall data from May 17th, 2020. So this is a model simulation snapshot there. And so this rainfall contributed to major flash flooding throughout Chicago and in other parts along the Chicago River. If you're familiar with Chicago, there's this beautiful promenade on the sides of the river that was completely inundated, led to a lot of damage there. And this was not an isolated event. The previous 3 Mays leading up to May 2020 all experienced record rainfall. So every consecutive year had experienced an extreme amount of rainfall for that particular month, 7 to 8 inches of rainfall. To give you an idea of how severe this particular event was, there was 3.53 inches of rain that fell in the Chicago area on the calendar day of May 14th. So this had, I believe, broken the previous record set in 1981 of 3.45 inches. So all in all, it seems like we're having a lot more frequent extreme rainfall events, and so this really underscores the need to have modeling capabilities that we can use to understand how this affects our structures that we build near water bodies. So in the context of this talk here, we're focused on the region between, forgive me if I'm mispronouncing this, Des Plaines River, extending down to the Illinois River. So this transitions. This is a complex transition zone with many different streams, creeks, and other tributaries that feed into this transition zone here. On the left-hand side, just for context, we have, once again, an orange blob indicating where we're looking at. So in the context of this, also, the other thing I want to point out is that the hydrologic units are the blue solid lines here. And our model domain, our focus area that we're going to be looking at later on is this black solid line. Okay. So during the event, there was around 30,000 CFS recorded at Des Plaines coming into the domain on May 18th. And on the outfall, we achieved around, it was observed around 100,000 CFS. And so from this point to this point, there was an incredible amount of confluence and conveyance of water coming through this river system. And what the other thing that's very interesting to note from these graphs is that we see that it's a very long-tailed process. It took very long, relatively speaking, around 2 weeks for the river stage, river discharge to decrease back to what it was on May 10th, for example. So in the context of this event, there is a recent project called the Brandon Road Interbasin Project, which is an ecosystem protection effort to prevent the invasive carp from traveling up the Mississippi and entering into the Great Lakes area. And this is a heavily trafficked waterway with a complex lock system. And the purpose of this project is to renovate this lock system and improve the ecosystem protection measures against these Asian carp that are coming into, that are migrating up into the Great Lakes area. And so this is our, as I said earlier, this is our 2D computation domain. Then we have a 3D inset. And so in this context here, we're actually going to be modeling both 2D and 3D, and each one has different applications. But the purpose of this is that our 3D area is essentially on top of the Brandon Road Interbasin project. So it captures the lock structure and the dam spillway that are there, so that we can get, so we can apply that to some more complex physical processes. So the rest of this talk is going to be focused on 3 different things. Firstly, we're going to be going over some of our numerical modeling capabilities and how we build these kind of models to do compound flooding and then nest it with 3D model. And we're going to be showing a demonstration case for the Brandon Road Interbasin project, and then briefly discussing some modeling implications and their utilities. So before I go into greater detail here, I just want to explain some of the flood drivers in greater detail, because I'm going to be using these terms throughout the talk. Probably the most commonly referred to flood driver is known as storm tide, storm surge. You probably heard it. It's associated with hurricanes when they make landfall. The action of winds and low pressure on the free surface cause a great deal of water to come on land and cause a great deal of destruction. Now, in the context of our location, there's no storm surge really. So the processes are really backwater effect due to winds over a lake, for example. So that's not really going to be directly considered here. But our primary interest is on riverine discharge, fluvial flooding. So rainfall accumulates into rivers in a upstream location, and then they travel downstream, leading to increasing the river levels and inevitably flooding the banks. And then the other process that we want to model is the local contribution of rainfall runoff. So you can think of fluvial flooding as the non-local rainfall runoff, and the pluvial flooding as local rainfall runoff flooding. And so essentially, this is when water can't infiltrate into the ground, and so it flows on top of the surface and takes the path of least resistance, entering into hydrological sinks. And this is a very complicated process to model because it depends on many different factors, including land surface roughness, soil moisture content, and the local hydrology of the region. So just in summary here, we're really focused on bullet points 2 and 3, fluvial flooding and pluvial flooding here. In other applications that we've done projects for, the primary focus has been on, for example, storm tide, storm surge, and we use these models that we're applying to the Brandon Road Interbasin area and the river area nearby to understand what areas are vulnerable to flooding during significant storms. So for example, we'll simulate a design condition or a 100-year storm or 50-year storm, and then look at how that actually floods the different streets and roads and waterways, and how that changes how much water actually accumulates in different areas here. So on the left-hand side, we simulated for a particular project, we simulated the remnants of Hurricane Ida and when they made landfall in the New York metro area. So we developed a whole model for that, and then we simulate that, and you can see that the water depths reach up to around 3 meters in some places. And on the right-hand side, there was a recent rainfall event that we simulated for San Francisco. We built a model for that location. And once again, you can see the total water level depth associated with that storm. So these models have a lot of, they're multi-use models. They can be applied for a variety of different reasons. But this is the traditional utility of these compound flood models. And the other thing is that they can directly interface between the land and the water. So in the case of a coastal domain where you have tides and storm surge processes, you can actually see the time evolution of the water as it penetrates into the streets and drains in and out of a back bay or an estuary. So this is, for example, during Hurricane Sandy in Jamaica Bay, you could see that this island here was completely inundated during the storm, and you can actually see the time evolution of the flow and how the tide influences that flooding pattern. But in the context of what we're looking at for fluvial and pluvial modeling, our flow is primarily driven by gravity and by accumulation of water in upstream watersheds as it drains out into the Mississippi River. And so here, what we need to do is we don't have any storm surge, we don't have any tide, so the problem becomes different to model, and we have to consider that when we're choosing, our tools that we're going to use and how we develop our mesh. For example, we choose our model domain based on the hydrologic units, so that we capture the inflows of various creeks, streams, and rivers into the major waterway here. And just to clarify, because sometimes the term model gets thrown around quite a bit, and sometimes it's somewhat ambiguous what it exactly means. In our context here, we're taking a numerical modeling approach. So we're taking governing equations that describe physical processes, and we're solving them using a numerical technique. Okay, so in order to do that, we need a mesh or a grid, discretization of our space, and we need a set of numerical routines that can solve the governing equations on that mesh or grid and produce a result. And so together, those two things, I refer to them as a model, and that's what I'm going to be describing later on. So in order to create the model, we need to build a mesh. And in the context of our simulations, we're using a finite element technique. And that requires to develop a unstructured triangular mesh. And before I go into in greater detail, I want to just introduce the concept here. And so what you see is a discretization of Galveston Bay. And depending on how you distribute these elements, it dramatically influences the fidelity of the model. For example, in the in the navigation channel that enters and exits in the center of Galveston Bay, if we don't have fine resolution in this place, then this channel is going to be aliased, and it's not going to be well represented in the model. In contrast, if we place fine resolution on that on that channel, then it's going to be correctly resolved, and we're going to capture the correct depth and the width of that feature. And obviously, that's going to have a lot of implications when we go to do our numerical modeling, both related to how accurately we've modeled the hydrodynamics and the physical processes, and also how long it takes to do. So when developing a model for this kind of approach, we have to be very careful with how we distribute elemental resolution and how we discretize the computational domain. So here at Baird, we have a lot of experience developing these models. Here are just two examples relating back to the two simulations results that I showed earlier with San Francisco and New York. We have on the left side New York. We can create with our tools incredibly high fidelity meshes going down to around 5-meter scales for New York and 10-meter scales for San Francisco that can resolve individual streets and model the flows associated both with rainfall, storm surge, and tides dynamically together. And so in order to do that, we have automatic unstructured mesh generation technology. And this is in contrast to perhaps more canonical techniques that use graphical user interfaces, such as SMS. The techniques that we use are involved with developing scripts, such as scripts in MATLAB or Python, and they rely on tools such as OceanMesh 2D, which I've developed, and now we collectively develop at Baird. And these tools help reduce model development times dramatically and also increase the reproducibility of the model generation process. And essentially, it boils down to 3 steps. Firstly, we have to collect our geospatial data sets, which is what you would do in the traditional kind of approach. However, the way we use those data sets may be somewhat different. Instead of actually opening up a GUI and tracing things by hand, we actually pass these data sets to what's referred to as an element sizing function. And we have heuristic relationships that we've developed that relate water depth, shoreline width, and other features to element sizes so that we can programmatically encode the element size of the model. And this enables us to develop models at scales that previously are not feasible to do using hand drawing techniques. Then we also have a module dedicated to post-processing so that we can prepare quickly the input conditions, whether it be boundary conditions, initial conditions, or just the input files for the simulation. And all in all, this reduces our model development time dramatically to get our first draft of our model. And so this is very important when in a context of a project where we have a tight timeline and we need to get out a result that's accurate, but also done in a timely manner. So coming back to our case that we're looking at here, in order to create the model, we need to have data to do that, right? And so the mesh generation process that I just described relies heavily on elevation data. Luckily for our case here, we have a great deal of publicly available data sets, so we don't have to purchase or buy anything from anybody. For this example here, we use the Illinois Height Modernization LiDAR dataset with some bathymetric updates from the Army Corps. We leveraged publicly available land cover use datasets and USA soil groups to develop infiltration maps, which I'm going to elaborate more on the next slide. And we have meteorological models that give us rainfall rate estimates. So for that, we're using stage 4 data from USDA, which is available on a 4-kilometer grid. And then lastly, to force our 2D model, we're actually using USGS stream gauges, which have QH rating curves. So we turn those QH rating curves into free surface variations. So just a little bit more detail on the infiltration map. We have codes that basically take the land cover data set and they combine it with the USA soil groups to create a curve number map. So in our case, we're modeling infiltration via a curve number approach. There's other possibilities to use, for example, a green and amp type approach. However, in this case, we're going to show the curve number approach. And so in order to do that, we need to consider antecedent moisture content and the land surface roughness thing. So we have an algorithm that puts that together and produces this infiltration map for us. Now moving on to actually creating the model, the first thing that we do is we create the mesh connectivity. Once again, we're using Ocean Mesh 2D to do that. And just to give you a context of where we are again, this top panel indicates the location on the map. So the orange blob shows where we are. And on the right panel is the orange blob blown up with our black outline and our 3D inset on the right panel here. So here we see that this is the triangle unstructured mesh connectivity. We see that there's incredible detail in the channels, creeks to capture the narrow waterways and the way the water flows into the major river body. And on the right-hand side, we have extremely detailed mesh and accurate mesh of the physical features like the lock and the vertical walls on the lock and dam spillway and some of these other man-made structures that are in the Brandon Interbasin project zone. Next thing we do is interpolate the topobathy data set to the mesh. So this illustrates how accurate that is. We have specialized routines to do that. On the right-hand side, once again, we do that as well. You can see that we're around 148 meters above NAVDA to around 164 meters. So there is quite a significant drop-off from the top to the bottom here. And then this is a map illustrating the size of the elements. So we're really going from 5 to 100 meters on the 2D domain side. And then for 3D, we're going from 5 to around, I believe, 20 meters size. And the one thing I want to point out here is that, especially in the context of 3D, we have to be super careful with how we discretize the domain. Because if we place fine resolution, for example, where my cursor is here, in the wide portion of the inlet zone here, then we're going to be, the cost to run that 3D simulation grows cubically. So we want to only put fine resolution where it's absolutely needed in the lock zone, capturing the flow over the dam spillway, and as we go into this narrower portion of the river. And in order to see how that looks, this is actually a simulation of mesh generation, which is probably something that you haven't seen. Here, what we're doing is the way Ocean Mesh 2D works is it actually starts from an initial distribution of points. And then what it does is it incrementally moves those points so that the element quality is very high quality which is amenable for numerical simulation. The other thing I want to point out is that we're capturing these constraints. These blue dots here represent point and edge constraints so that our mesh connectivity is automatically aligned to those vertical features, such as the dam spillway or the vertical walls and the lock gate. And the reason for that is if we alias those elevations on this vertical crest, then the flow may pass through and create erroneous hydrodynamics. And obviously that's not what we want. So we have to be very careful when we're building this model. And just once more, elaborating more about the 3D model, it uses a sigma coordinate system in the vertical direction, vertical axis. So in this case, for our project, for this case study, we're doing 10 vertical layers, and they're time varying following the free surface. Now, I will point out that this image is not the variation of free surface in time. This is just plotting each one of the 10 layers in a sequence so that we can see how the 10 layers, how each layer looks in the model. And so what you notice is that as you go into shallower depths, the layer resolution decreases, and then as you go deep water, vice versa. To do the modeling, we use a modified version of telemach. Telemach has been used for other Army Corps projects in the United States, as we are aware. Telemach is an open source model since 2010, and it has dozens of features as part of a suite which has water quality modules, 2D modules, 3D modules, etc. We have leveraged that and developed additional capabilities in-house. In terms of what it does, it solves nonlinear shallow water equations in 2D and not Navier-Stokes in 3D, the Reynolds average Navier-Stokes, in a way that conserves mass, which is obviously very important for a number of applications, and it uses finite elements, as I previously mentioned. Some of the select features that we've improved on are time and space varying wind and pressure. We have parametric models for wind and pressure, and also we can force measure data. And also we have time and space varying rainfall with either the two infiltration models, the curve number or the Greenland-based approach. There's also a number of other features. Here's just a list of some of them that we've included into the model. Drogue release, we've done some stuff with prop wash and prop scour, dye release, sediment transport, and general improvements to the computation performance to make it feasible to run for project-based workflows and project-based timelines. Okay, so now coming back to our case, once again, we need to have boundary conditions and initial conditions to force our simulation. So we have 7 locations where we're forcing the 2D domain with other rivers we've identified. So you can see those with the arrows. Those indicate the direction the flow is traveling. So what you see from this figure is the discharge curve as a function of inlet location. We have 100,000 CFS, as I said earlier, exiting the Illinois River and around 30,000 coming in. So all those other contributions are either coming from rainfall runoff, which is trickling down into the waterway, or from accumulation into these 5 other creeks and rivers. So we're modeling each one of those inside of our 2D model domain. And now one of the challenges with doing this modeling is that we don't have a good free surface gradient initial condition. So we have to estimate that. The way we do that is by taking the entire domain and putting 1 meter of water on it and letting it drain into the hydrological sinks and reaching a steady state condition. And then we stop it, and that becomes the initial condition for our 2D simulation. So this allows us to get a realistic free surface gradient at the start of our event without relying too much on available data sets, which sometimes are hard to come by for the free surface gradient. Okay, now here's the grand finale, so to speak. This is the final, this is the animation of the event happening. So we're showing the accumulation of water due to rainfall. As you can see, there's burst of rainfall. It was a flash flooding event. And then that rainfall eventually trickles down into the waterways and the pluvial component trickles down into the waterways and then leads to flooding, especially downstream in this area. You can see here. The focus region for the 3D model is over here, but so what's happening here is that 2D contribution of pluvial contribution is actually increasing the stage level and also increasing the flow velocity through the river. So we're capturing both the discharge effects and the pluvial component in the model. And what we do is we take the boundary locations of our 3D mesh, and then we use that to extract data from the 2D results, and then we force generally a shorter time period around the peak of the event. And this is really because the 3D component of this is much more expensive than the 2D. And we can't simulate for very long periods of time, generally speaking. So we just focus on very important time periods. So for example, here's right on May 18th during the peak flow through the Brandon Road interbasin area. You can see that as the water reaches a certain height, it eventually overtops the spillway. You can see the vectors indicating there. And then you can see just incredible flow velocity through the lock, which we've decided to leave open in this hypothetical scenario. But in practice, what we could do is actually model various scenarios, extreme scenarios, or normal ambient operating scenarios with this kind of modeling configuration. The other application that we leverage when we do 3D modeling is typically prop wash and prop scour. And what this is showing are two synthetic passages of tug barge vessels going through the Brandon Road interbasin area. These are not real tracks, I will say, but they illustrate the speed associated with the propeller in the water column there. So these animations are in sync. What you see on the top is depth average, and what you see on the bottom right is at each layer. And this is a very useful thing if you want to, for example, analyze wake generation, or if you want to look at prop scour that's caused by the prop wash. And also in the context of this particular area, it's one of the most heavily trafficked water bodies in the United States. And so to really understand the impact of the ship movement on the canal, on this area, you need to do something to this level where you're looking at what the velocity is coming off these ships. One of the other major applications of this kind of modeling is sediment transport. So here we don't have the borehole information we don't have good borehole information at hand that we could apply here. So we assumed an initial distribution of non-cohesive sediment, and we ran the model and we look at how the bed erodes and changes throughout the peak events during the peak flow conditions. And so what we see here in the color is how the bed can evolve. And this has a number of use cases as well, which I'll elaborate in the next couple slides. And then one of the other major applications is dye release. For example, here we're releasing two dye locations here, one here and here, and this is passing through the lock zone. This is very important to understand the fate of certain suspended materials in the water column. This is a very short animation. It's every second, I believe, being plotted. So you can see on these two plots the cross-sectional area. So the vertical axis is depth, and the x-axis is time. So we can see how the concentration varies as a function of time, given these two dye injection locations. So all in all, in summary here, the utility of these capabilities is that we can model the erosion, resuspension of bed sediment. We can look at wake generation and see how that can influence the design of structures. We can model prop scour to see how the bed may change as a result of the repeated passage of a certain kind of vessel. For dredging maintenance and operations, these models are essential to understand how the channels are going to change and what's their health. And then lastly, the fate and transport of materials in the water. So in the context of the interbasin, Brandon Road's interbasin project, water released from the lock, it's important to understand where that goes. That can contain material in it that's toxic or potentially hazardous for wildlife. And so it's important to understand how that propagates downstream the river, and the overall hydrodynamics in the approach channel as well. So the major takeaways here are, just how we highlighted how we can improve the modeling workflows with this advanced mesh generation techniques, how that can be used to develop 3D models and 2D models, and how they can be interfaced together. In our 2D case, we're modeling the contribution of rainfall runoff and riverine discharge, and we're using that to force our 3D model. And then the other major point of that is how we can apply these models for different engineering applications. And I gave you 3 different applications: dye release, ship transit, and a vessel transit, and what was the third one? Then the hydrodynamics in the channel associated with the 3D model. So that's all I have for now. If you have any questions, please feel free to post them, and I'd love to answer them. Thank you all for listening.
Excellent job. That was good. I'm glad
Thanks.
that the actual models worked. I was worried maybe the video wouldn't work, but that looks great. Fantastic. So how has that changed your life from a standpoint of this modeling, the technology?
So in terms of having these capabilities, so it allows us to prototype designs faster, and it allows us to, especially in the context of the incremental design and build type study, it allows us to investigate different scenarios in a more reliable way, and in a way that's repeatable, which I think is the most important thing. So typically when you build a model by hand, there's a lot of assumptions that go into that development process, and having tools that you can script that generation specifically with respect to the mesh generation side of things, that improves the process a lot. We find, at least, it makes it more objective. And actually, the other aspect is model stability. If you go and develop a model, for example, by hand, sometimes what happens is you violate some numerical constraints, and that leads to bottlenecks in the process, and then you have issues where it gets very stressful because the model's not functioning, as you just mentioned, and you'll have nothing to show. And so having tools like this greatly reduces that problem.
Oh, fantastic. Brad, is
Ted, if I can add
any
to
other
that.
questions? The audience have any? Oh, please.
So another advantage of doing this at the mesh generation side is making things very efficient, but also using the integrated modeling system, that is, having the fluvial storm ties, you name it, all in the same model, actually makes it more objective compared to coupling separate models in different length scales, basically. It's a very hard thing to do, where you merge 2 models which feed into each other. So we're completely eliminating that by running the pluvial and fluvial and storm tide all in the same model.
Yeah, it's a very good point. I just want to add one thing to that, is that you typically have this division between the hydrological models and the hydraulic models and the coastal flood models. And yeah, having integration between them so it's seamless is a big advantage, because, for example, those animations I showed of Hurricane Sandy, it's very arbitrary where you put the boundary, and the boundary changes between the 2 flood zones in that context, because you have, for example, a storm surge happening, it's propagating inland, and then your hydraulic your HEC-RAS model, or whatever you're using for the overland flooding stuff, may not line up with that boundary, and so the boundary conditions may not be representative of what actually happens when you have that separate modeling capability, when they're divided like that. So this is really, that's why we tend to use the phrase integrated, because it's combining the physical processes into one model.
And as you said earlier, you have to have the data in order to be able to do very accurate modeling. And so how hard is that to mine that data? I mean, that seems like I'm not obviously an expert in what you presented, so it's very, open. to me, but how hard is that to really refine that data to make sure you have those good models?
Yeah, so that's absolutely right. Everything is predicated on good data. Luckily, in the United States, it's a gold mine for good public data, especially for the context. I'll give you an example for New York City when we did that case when we were representing all the buildings and all the streets. That data is all publicly available, and so you can download it, and then it's in a common GIS format that almost any GIS expert would be able to pick up and figure out how to use. And then that can be directly integrated into the mesh generation process. So I would say in the US, it's fairly good. I know obviously as you exit the US, you go into, for example, the Caribbean and some other places, it becomes an issue. But still, then what you can do is leverage surveys and try to create DEMs from those surveys. But it's a challenge, and yeah, that seems to be the limiting factor at this point for other places around the world. So in the US, it's great though.
If you know how
Speaking.
to get it, right?
If you know how to get it, yeah. I
If you
mean,
know how to get out there. But that's always a challenge too. So
it's a
you know how
challenge.
to
Yeah.
get it. So that's great. Well,
Yep.
fantastic. Is there any other questions?
Hey, Thad, we did actually have a question for Keith
Awesome.
and Enter. What's the process for calibrating these models to known events, and are there any tools to make that process easier?
Let me think here. Generally speaking, it depends on the application. For the 2D compound flooding, for example, when you're validating fluvial or fluvial integrated model, you have to have high water marks you could look at to see what the extent of the flood was. We've done that in the past. Besides the gauges, for example, NOAA sites, you could compare water level time series. For USGS, there's a lot of these streams are gauged, so you can compare with those stream flow gauges and see how well the model's doing there. I know we didn't touch on the calibration side of things. In terms of the tools, not too familiar with. I would say that I typically do everything by Python. I mean, in terms of the codes, everything is done at a scripting level. So we typically find, some packages like use leverage as commonly used publicly available open source Python packages and write codes that compare these things together. But I'm not aware of a single package that facilitates model validation. No.
So I guess if the question is about if we have something like Ocean Mesh 2D that we use for mesh generation, we don't have a package like that we use for calibration. As
No,
Keith
yeah.
said, we just use MATLAB, Python codes, simple comparison codes, basically.
Yeah, but it is an ongoing challenge to validate the rainfall runoff because not everywhere has observations of a particular event. So that's an outstanding challenge often that we face is understanding that. But generally, if you're getting the stream flow correct, it's somewhat implicit that your model is functioning correctly because that water is inevitably trickling down into those waterways. So that's all I would say about that. But the rainfall infiltration rate side of thing, that's very hard to validate. I'm not aware of how one could do that.
Excellent. Thanks for the response, and thanks for the question, Daniel. I guess I had a question too for the New York model. Was that was one that you guys built too? Was that used by the city of New York for some of their decision support systems, or what was the application for that model?
So, Owner, do you want to answer that one?
Sure. Yeah. Hi, Brad. That model was built solely for presentation to the New York City DEP. That could be, so their feedback was when we showed that, was that, what the run times are, or can this be used for forecasting? So that's that's why we built that model. That's a 10 million element mesh. It's a big model. It has all 5 boroughs to the street level. And we were running Hurricane Sandy and the remnants of Ida together, combining them. What would be the impacts of that? So we were looking at that. Just to give you an idea, since I mentioned the size of the mesh, the run times, I guess is important. That one was ran on a older desktop computer on 28 cores, and it's a 3 days event, I think, that we simulated. And it took 1.5 days to run it on an old computer. For forecasting purposes, we benchmarked it in our cluster with 160 cores, for example. It runs under 4 hours. So for forecasting, they were saying that's very useful because that could save lives if we can run 3, low, mean, or high forecast of rainfall, for example, and we can deliver that under 12 hours, then they can actually prepare for that. So it's a very robust model in terms of its computational efficiency.
Mhm.
Yeah. Yeah. Excellent. Yeah. Thank you. It sounds like a really powerful, incredibly comprehensive model. Be
Yeah,
awesome.
I just wanted to add to that. Basically, the one major advantage well, one of the major advantages of telemach is wetting and drying in the model. I've used many numerical models in the past, and the biggest holdup tends to be how flooding happens. Flooding and drying actually propagates, and how that moves. And sometimes mass isn't conserved, or mass is erroneously added to the model when it's generated when it shouldn't be. And so telemach does a fantastic job. It's one of the best models that I've seen in that capacity. So one of the reasons why we use it to do something as such as like a 5-meter compound flood model of New York City is because of that, because it's just a tremendous amount of wetting and drying processes occurring. And if you're using another model, it could go numerically unstable, and then you don't get a forecast. And so we find that this model tends to be a lot more stable, and that's in conjunction with how we design the mesh, right? So it's not just the numerics are good, but it's also that we're building the mesh in a specific way so that we know, this, if we represent this feature in this way discretely, it's going to be a problem. If we do it like this, not going to be a problem. So that's kind of why, that's our logic behind why we selected this tool.
Well, great job. Thank you very much. Really
Yeah, thank you
appreciate
very
you
much.
guys' time. It's you tell your presentation was really well thought out. And so please, if you get an opportunity, please check out Baird.com. Look at their website. Here's their email addresses. They aren't Albert and Eric, so but so that's an inside joke.
By the way,
Email them.
Keith, I think your email is not correct.
So
Oh, wait,
on the
wait. Yeah,
screen.
that's missing a T there. So it's K Roberts
Oh,
TS.
we'll
That's
make
right.
sure that we get the right ones out to everybody as well before we publish anything. But please reach out, email these guys. Obviously, you can see they know what they're doing. So excellent presentation. Really appreciate you jumping on, and
Thank you.
have a great weekend.
You too.
Thank you very much.
Thank you. Let me stop sharing.
Hi, Kyle. Are you guys all together?
Right now, it's just me. I was just
Okay.
messaging Dave. He should be on pretty soon.
Okay. So you, Dave, and is Derek going to join you as well?
Unfortunately, the tribe that he works for, the leadership, has called him off to another meeting this afternoon.
Okay.
So
Yeah.
we'll
No
cover
problem.
his slides.
Okay. Sounds good. Are you sharing your? It's going to be yours. Okay.
Yes, I'll be the one doing the sharing.
Okay. I'm going to make you the presenter just so you can do a little dry run here, and then you can see if it pops up for you. Thank you for doing this.
Yeah. Let me. All right. Sorry, I was getting all my
Nope, don't
windows
worry
and my
about it.
ducks in a row here.
WebEx confuses me. Just got used to Teams and now.
I feel the same way.
Doesn't take
All
much
right,
to
let
confuse
me-
me though, so that's not saying much.
I was everyone I've talked to at the federal government says WebEx just doesn't break. It doesn't have all the fancy features, but it's pretty reliable. So except for
yeah,
we'll start at the beginning of our slideshow.
there you go.
Spoilers for everyone sitting on the other side. Sorry.
I closed my eyes.
All right.